Welcome to the Interthread Communication section of this course. Interthread communications is handled by an external logic block. It is connected outside of the core. This block connects to the cores through the gating storage interface. You can design your own ITC block to do exactly what you want it to do, but this section deals with the ITC block that has been designed by MIPS and is part of your core package. The ITC block is grouped into elements called cells. Two kinds of cells are supported. A FIFO cell that contains 4 32-bit entries and a semaphore cell that contains 1 entry. All cells can only be accessed by whole words. In other words, you can do a 32-bit load or store to a cell location. Each cell contains a tag entry that tells you about the cell and allows you some control of the cell. The tag entry is accessed through the control view, which I'll go over later. The FIFO def field will be set to 0 if this is a semaphore cell, or 2 if it is a 4-entry FIFO cell. The PTR field will always be set to 0 if this is a semaphore cell. For a FIFO cell, it indicates the number of cells to read before the cell becomes empty. The FIFO field will be set to 0 for a semaphore cell and a 1 if the cell is a FIFO. The trap bit will cause a gating storage exception if the thread accessed the cell through a PV or EV view. This can be used by an OS to swap this thread out for another. The F bit will indicate the cell is full. The E bit indicates the cell is empty. Software can set this bit, making the cell empty, which will also reset the cell's pointer, so this is a quick way of clearing the cell. A view is the method the thread wants to use to access the cell. The ITC controller will look at bits 6 through 3 of the address being accessed and use them to figure out how the thread wants to access the cell. The next several slides will go into detail about each view. The bypass view is used to bypass the normal operations of the cell. Loads or stores do not cause the issuing thread to block, and the cell's state bits stored in the cell's tags do not change. For a FIFO type cell, a bypass store overwrites the newest FIFO entry and a load returns the oldest entry. You would use this view to set the initial data values for the cell. The control view is used to change the cell's tags without any other effect. All tag loads or stores will write the entire 32-bit value. A load or store to a tag will not cause the issuing thread to block or cause a gating storage exception. If you use the control view to set the empty bit, the FIFO pointer also gets reset, thus clearing the FIFO at the same time, so you don't have to read out all the FIFO locations. The empty full synchronized view is used to write 32 bits of data to the cell. If the cell is a FIFO, the data is read in a first in, first out manner. Reading an empty cell will cause the executing thread to block until something is written by another thread to the cell. Writing to a full cell will block until the cell is read by another thread. The empty full bits of the cell are evaluated and updated appropriately with each load or store to the cell. You should not use the store conditional instruction with this view. If the trap bit is set, any access will cause a gating storage exception. This can be used by an OS to reuse the threads that would normally be idle waiting for something to be written to the cell. The OS would have to save the context of the thread, then it could use the thread for another process. When new data is written to a cell, another exception would happen and the OS would know that it needs to find a thread to continue processing. The empty full try view is similar to the previous empty full synchronize view, but it is intended to work with a load link store conditional instruction. Instead of blocking, a load will return a 0 if the cell is empty. A store to a full location will not block but just fail silently. But a store conditional instruction can be used to tell if the store succeeded or not. The PV synchronize view implements a PV counting semaphore. A load will block if the semaphore value is 0 or decrement the value and return the old value. A store does not actually store a value to the semaphore. Instead, it increments the value in the semaphore. The empty full bits have no meaning when using this view and are not updated. Do not use this view with a FIFO cell. If the trap bit is set in the cell's tag, then any access will cause a gating storage exception as discussed in previous slides. The try version of the PV view never blocks. If the cell value is 0, a load will return a 0. Do not use the store conditional instruction with this view. If the trap bit is set in the cell's tag, then any access will cause a gating storage exception as discussed in previous slides. The ITC block contains two tags that can be used to read the current configuration and configure the ITC block. To access the ITC block, you need to set the ITC bit in the CP0 error control register. This will direct the cache instruction to the ITC block instead of the cache block. Here is an example of the C code needed to set the ITC bit. To read a tag, use the cache index load tag instruction. To write a tag, use the index store tag instruction. There is an example at the end of this section that will show instructions needed to read and write these tags. The first ITC tag is located at offset 0. It contains the base address of the ITC block and the ITC enable bit. The base address should be set when you initialize the ITC block. The address uses the top 22 bits of this register, along with the address mask that I'll explain in the next slide, to determine the starting address of the ITC block. The ITC enable bit enables the ITC block. This should be set when you want to start using the ITC block. Note, if you position the ITC block over real memory or device I/O memory, you will no longer be able to access that memory or device. The second ITC tag is located at offset 8 and contains the number of ITC entries you have, the address mask, and the cell entry grain. The number of ITC cells is static for your core and this field can tell you how many you have. You can set the address mask field. This is an address mask. It indicates which bits of the base address field should not participate in determining an ITC memory hit. This field effectively defines the size of the ITC memory block. Adder mask set to 0 implies a 1K ITC address space, and adder mask set to 3F implies a 128K byte address space. You can set the grain entry to configure the interval spacing of the ITC cells. This chart gives you the entry value and the corresponding interval. Here are some ideas of what you would do about the entry grain value. For simple semaphore cells that are used to communicate between processes and the OS, you would probably want to space them as tightly as possible to save on memory space. For FIFO cells that will be used to hold data within a process that will not be shared with other processes, you can space the cells wider apart on different pages so the cells can be mapped to the processes and protected by the TLB. One thing to take into account: depending on the setting of the address mask, number of entries, and entry grain, it is possible that ITC cells do not fill up the entire ITC address block. For example, if you have only 2 cells and they are mapped to a 1K byte area with a stride of 256 bytes, the first cell starts at offset 0 and the second cell at offset 100. The remaining two 256 byte regions starting at offset 200 and 300 do not map to any storage. Any access to an address that does not map to an ITC cell will result in undefined behavior. It is also possible to set the cell entry grain too large for the address mask, which will make some of the cells unavailable. Once the ITC enable bit is set in the tag register, all accesses for the memory region will go to the ITC controller. Anything that was in that address range will no longer be accessible. After you are finished initializing the ITC block, make sure to clear the ITC bit in the error control register so cache instructions will once again be directed to the cache controller. I am now going to go through and tie this all together with a code walkthrough of the use of the ITC block as a semaphore. In the example, I will use 4 threads on one VPE. I will use the PV view for the semaphore. In this simple program, each thread will acquire a semaphore, count to 2000, and then release the semaphore so another thread can count. I will go over the code changes made to the basic thread example I showed you in an earlier section. First, I'm going to configure the ITC block. To get to the ITC block controller to configure its tags, you need to turn on the ITC bit in the error control register. Once you do that, you can use cache instructions to read or write the ITC block's tags. Here is a sequence of C instructions to turn on the ITC bit configuration. As you can see, I use the MIPS32 get error control macro to get the register. Then I turn on the ITC bit using the error control ITC #define. And last, write the error control register with the new value using the MIPS32 set error control macro. Now I am set to configure the ITC's address mask and entry grain. Since I'm going to use the cache instruction to write the ITC tags, I must first set up the data tag low register with the correct information. The cache instruction will write the value in the data tag low register to the ITC tag. Here is the code to set the address mask and the entry grain using the pound-defined values for the address mask and entry grain. This code moves the values to the data tag low register using the MIPS32 set data tag low macro. Now that the data tag low register is set up, I can use the cache instruction to write to the ITC's tag register. I will use inline assembly code to do that. You can see the cache instruction takes two arguments. First is the command operation you want to perform, which in this case is operation 9, index store tag. The second argument, which is the location within the ITC tag memory you want to write. In this case, I'm using GPR0 with an offset of 8 bytes to write ITC tag 1. Now I'm going to configure the ITC tag 0 with the base address of the ITC block and enable the ITC block. When I reserve space for the ITC block, I just declared an array. I did this to make sure that other variables would not be placed in that memory mapped range. I could have just selected a physical address that's not mapped to any device. But because I declared the ITC block as an array in C, it is given a virtual address in CaseEx0. Since this address in CaseEx0 is mapped to a physical address starting at 0, all I need to do to convert this virtual address to a physical address is strip off the top bit. Next, I OR in the enable bit. Then I write the value to the data tag low register using the MIPS32 set data tag low macro. Now I use the cache instruction to write the data tag low register to the ITC tag 0, the same as I did for the ITC tag 1, except this time I use the offset value of 0 for tag 0. Now that I am done writing the ITC block tags, I will turn off the ITC bit in the error control register so the cache instruction operation will refer to the cache instruction instead of the ITC controller. So far I have enabled the ITC block but not the actual ITC cell I will be using. To do this, I need to use an uncached address to access the cell. I can do this by changing the address of the cell array from being in CaseEg0 to CaseEg1. Here is the code to do that. Now that I have the correct address, I need to set the lower bits of the address to tell the ITC controller which view I want to use. To enable the cell, I need to set the enable bit, and to do that, I need to use the control view. So I set those bits. Then I write the enable bit to the cell. Since I don't want the semaphore to block the first time through, I want to set the cell to start out with a 1. To do this, I can just use the PV sync view, where any writes to the cell will increment its contents. So I OR in the PV sync view bits using the pound-defined ITC PV sync view and write to the address. In the count function, before we enter the counting loop, I want to add the code so that not more than one thread will be counting at a time. This is where I will read the cell using the PV-Sync view. To do this, I OR in the PV-Sync view bits into the cell address and then read the cell. Since I initially incremented the cell, the first thread to get to this point will get the semaphore and decrement the cell counter to 0. The next thread reads the cell block will block, waiting until the cell counter is incremented before it can continue. Then I add code after the count loop to write to the cell. This will increment the cell to 1 so another thread can continue using the count loop.